In this video, we look at confidence intervals. We'll first look at confidence intervals for means, and then later in the chapter we'll talk about confidence intervals for proportions. So the idea of a confidence interval, sometimes called interval estimation in statistics, is we start with our point estimator, our best guess, usually our sample mean or our sample proportion. And then we look a little bit above that estimate, a little bit below, to account for variability and sampling variability. So a confidence interval for a mean is a computed interval comes from sample data. The idea is we construct this in such a way that if we were to do this over and over again, C is the confidence level, and it's the proportion of these confidence intervals that would capture the true population mean. And so when we draw our conclusions, we can say we're 95% confident or 99% confident that the mean is in a particular interval. So with confidence intervals for a mean, we utilize the sample mean. And confidence intervals for mean look something like this. We start with x bar, our best guess, our sample mean. And then we're going to go a little bit above and a little bit below, hence plus or minus e. This e here is sometimes referred to as the margin of error. And it depends on the sample size, it depends on the variation or variability in your sample data and your population data. And it also depends on the confidence level that you're interested in. So confidence intervals for a mean. First, we'll look at the case where we assume the population standard deviation is known, sometimes called a z-interval. This is really the more unrealistic case. If you think about it, we are trying to estimate the population mean. Remember, the population is the whole group we're interested in studying. And we're going to draw these conclusions based on sample data. So it seems a little unrealistic to assume we would know the population standard deviation and not know the population mean, which is really what we're estimating here. So a lot of statistics textbooks will present this, but this is really the unrealistic case. But notice we have x bar plus or minus e. In that margin of error, there's a z value that comes from the table. And essentially what that z value is it's the critical values that give the middle percentage off the standard normal distribution. So if I want a 95% confidence interval, those z sub c values are going to be the z values that give me the middle 95% in the standard normal table. N is obviously sample size, and here sigma, of course, is that assumed standard deviation. Now the second case is what's called a t-interval. And here we don't assume we know the population standard deviation, but we estimate it with our sample standard deviation. So this is the sigma unknown case. There's a typo there. That should be sigma unknown. So t is the critical value now from the t-table. It's very similar to the standard normal table. It's centered at 0, normally distributed. Remember, you look up a degrees of freedom when you look up a value in the t-table. N is still your sample size, S is the standard deviation. So again, case 2, we're assuming sigma is unknown here. And this is the more realistic case. Our entire interval then is based on sample data. The sample mean x bar, the sample standard deviation S, the sample size N, and then that value from the t-table. So if we look at critical values real quick here. So with the z distribution, your table has a little table right next to it that has confidence level values for various values of c. And it tells you what these values are. But basically what it's doing is it's finding a middle percent. So if I wanted a 95% confidence interval, the table says it's plus or minus 1.96. Why is that? Well, if you were to look up the plus and minus 1.96 in your z table, those are the z values that give you the middle 95%. If I wanted a 99% confidence interval, plus or minus 2.58 gives me the middle 99%. So that this little table here at the left of your complete table kind of does this work for you. But you can use the table and find any confidence level. I mean, you could find a 92 or an 86% confidence interval. You're just looking for those z values that give you the middle percentage. The t-table, remember, is a little different. The standard normal table, the z-table, there's just one table. The t-table, there's multiple t distributions, each with an associated degrees of freedom. So if I had, say, a sample of size 7 and I wanted a 90% confidence interval, here's how you would use the t-table. Your degrees of freedom, remember, is sample size minus 1. So 7 is our sample size, so our degrees of freedom would be 6. So I would go down to 6 degrees of freedom along the left column, then across to 90%. And those meet at 1.93, and so that would be my T critical value. So let's look at some examples. First, the case where sigma is assumed known. So suppose we have a group of college students, and the average number of hours spent studying for the final exam is 4.35 hours, and we're going to assume the standard deviation is known to be 2.67. So if I want to construct a 90% confidence interval, I have assumed sigma is known, so I can use a z interval here, x bar plus or minus z times sigma over the square root of n. So now it's just a matter of plugging in my values. If I plug in my sample mean, if I go to my z table and find the value for a 90% confidence interval, it's 1.645. My standard deviation is 267 divided by the square root of 20. So if I multiply all those things together, I get 4.35 plus or minus 0.9821. So to construct my interval, I take my sample mean plus 9821, then I take my sample mean minus 9821, and hence I get a 90% confidence interval. So I'm 90% confident that the average number of hours spent studying for the final is somewhere between 3.36 hours and 5.33 hours. There's a confidence interval where we assume sigma was known. One other thing that comes up with confidence intervals is oftentimes we talk about what sample size is needed to get a certain degree of precision. For example, suppose we have a survey of college grads and the average salary was $45,943, and we'll assume sigma is known to be 69.89. So if I wanted a 98% confidence interval, I would use that exact same formula, x bar plus or minus e, plug in my 45,943. If I go to my table, a 98% confidence interval, the z value is 2.33, standard deviation over the square root of n. So I'm 98% sure the average salary of a college grad is between $41,871 and $50,014. Now, suppose I wanted that interval to be more precise. Right now it's about $46,000 plus or minus about $4,000. Suppose I wanted to be more precise and I wanted to estimate this mean plus or minus no more than $1,000. Well, there's a sample size formula in your textbook, and essentially what we're doing here is we take that expression for E and we set it to $1,000 and solve for n. Figure out what n I would need to get that degree of precision. So if I plug that in this case, the z is 2.33, my standard deviation, and I want a margin of error no more than 1,000. That's my E value here. Notice I get 265.18. So I would need at least 265.18. Well, I can't get a partial when I'm doing a sample, so I round up. So if I took a sample of 266 or more, I would guarantee that my confidence interval would be plus or minus $1,000 or less. So this is very common in statistics, because if our intervals are too wide, they don't tell us anything. We can't interpret or draw any conclusions. So oftentimes statisticians start by figuring a sample size needed for a certain degree of precision. Last example then would look at a confidence interval where we assume sigma is unknown. So this is going to be the T interval. So a survey of certified public accountants, we found a sample average of 69.68 and a sample standard deviation of 78.92. So a 98% confidence interval. So here, notice the confidence interval is very similar, only now I'm using a T distribution and my sample standard deviation. So if I plug in values here, and that T value came from the table, 98% confidence with 24 degrees of freedom. If I plug all those numbers in and go 69.68 plus 39.33, 69.68 minus 39.33, I get this confidence interval. So I'm 98% confident that the average salary of a CPA is between $57,000 and $65,000 roughly.